then if you miss the first class, it will be fine, and if you miss the first few minutes of the class, it will. Then let's recall the last thing that we were doing. We defined the Fourier transform. Then we discussed several properties. The property that we care the most are the one that we are going to repeat today, and we will see that immediately that will bring you some open questions for Schrodinger equation. But we have to wait a little bit. Something. Then some results. Let's call this. Suppose that F is in L1 and have fast decay. I mean, it's in L1 with this measure. That means that you are integrable with something that grows at infinity. Then the Fourier transform have analytic extension okay, let's assume that we are in one dimension to make it simple, but okay, and I think it's too high over it. Okay, let's see the proof of this, that is very simple. You have this formula. This is an analytic function. The question is this integral make sense of this summation if you want to think? Then you write, let's do it in one dimension, but it's true in any dimension. You put absolute value, you see that this makes sense if this in therefore, this is defined is this quantity is less than epsilon. Right? Then is 2 pi, this is less than epsilon, you are okay. Then this is the other way around. Then you are analytic. Like this. Then this is another way to say that if you decay very fast, exponential, your function is extremely regular. In particular, it's analytic. Okay. This is clear. I mean, you can state that in n dimension the same, right? Then if you decay against exponential, then you have an analytic extension. In particular, you have this. If F, let's say that I have compact support, then we know that if you are in the C-infinity function with compact support, you are Schwarz, then the Fourier transform will be also in the Schwarz class. What you have is that you will then you can, if the function have extremely fast decay, you have compact support. The Fourier transform cannot have fast decay. Okay? Why? Well, if this function were in L1 for some epsilon, then the Fourier transform of this one, that is the F, will have an analytic extension. You cannot be analytic and have compact support at the same time. Right? Then the theorem proof if then has an analytic extension. But then F already has compact support. Then the only function that has compact support that is analytic is the function 0. Then suppose that you put here F is not 0. Then you are in the Schwartz class, but you don't have exponential decay. Then the theorem that we saw that characterized completely what is the Fourier transform of function that has all the derivatives and have compact support is the Paley-Wiener theorem. That say if F is infinitely compact support, the support of F is contained in the ball of center 0 and radius r, then for all n, F has an analytic extension to the whole Cn, and you have this estimate. These estimates tell you that you have the polynomial decay because you are in the Schwartz class, and you have the grow. If when you extend it, it grows accordingly to the complex part of the extension. And if you are real here, you just have a polynomial bound in the denominator. You don't have anything better than that. You cannot expect to have exponential decay with respect to C. Okay, this is the last things that we cover, and then we start with uncertainty principle. And again, all this we covered last time, right? Okay, the first uncertainty principle that we did was Hardy, and say that if f of x is a Gaussian of this form, and the Fourier transform is of this form, and A with A and B positive, then if A times B is more than 1, you are 0. If A times B is 1, you have to be that tells you that this is the, put a limit how fast the Fourier transform and the function can decay. This have been extended to Rn and LP setting. This is what for Tangabello, this is though for Cowling Price, and what this is say is the following. Suppose that you have the function multiplied by A pi x squared, and suppose that you have this. And P and Q are not dual. If one of them finite, if A times B is more than or equal to 1, then you are 0. Okay, this is, you are set, you don't, here, because you are in L infinity, where you care, you don't have the quality here, the quality is included, you have to be integrable. This on decay. Okay, and in some moment will be clear why we are so concerned with a certain principle and what is the relation with the Schrödinger equation. That's not clear at this point, right? But it will be, and we will see that in an hour we will stay at least an open question, something that is unknown. Okay, but we have to motivate, because most of the tools that we use for this are completely useless for what we want. But let's stay with this, and let's go with Berlin-Hormander result. Berlin-Hormander said the following: suppose they prove it in one dimension. If F is in L1 and you have this elegant formula, okay, this is a, if you put this weight, you're in one dimension, if you put this weight and the product of the Fourier transform and the function is integrable, again, this weight in R2, you have to be 0. Okay, this is very elegant, and you will recover this result with, if you, some remark, if you use that 2x multiplied by y is less than x multiplied by a plus 1 over a multiplied by c square, then you will recover this result. Then you prove that if f of x exponential of a pi x squared, we are in one dimension, and A and B positive. Then this condition implied this one. Or this condition and this one imply this one, then you recover this part. Okay. Okay, before we go, since Didier said that he would like to see the proof of this, and it's, I mean, for general culture it's okay, but you will see that it's not, I don't know how to use that in the setting that we would like to, but that's okay. Suppose that we generalize this. And you put here, you can go with John inequality. You have that x multiplied by c is less than x to the p C to the Q, Q, and then you have the following. This implies the following. If you can put some constant, let me get the constant right. Okay. This is a 2 because you didn't remove the 2. You have this. You can put A here to the P. You can put 2 pi B to the Q, and the condition that you have is A and B are more than 1, and A and B are positive, then F is 0. If you use Young and then you put the A multiplied by 1 over A, and you use the trick that we use here, you have that this condition implies this 1, then you are 0. And then you can ask, is this sharp? Well, this is sharp. This is sharp when this one is sharp when you're using 2 and 2, but this one, if you use 1 over P here, but 1 over Q equal to 1, this is not sharp. The further away that you go from 2, that is not sharp. What is sharp is this one. This is not the right condition. The right condition is this one that is due to bon ami. Demanje and Jamin. And the condition is this one, that A times B has to be larger than the absolute value of the cosine of pi over 2, 1 over P, implied F. See, if P is 2, you get 1. That is what you have before here. But then, of course, if P is not 2, I mean, P is the one that goes below 2. Then when P starts to get very close to 1, you can go down here. This number is smaller than 1, right? Therefore, you are accepting that this, okay? And this is sharp. If you have the quality, you can find this. Okay. Okay. If you can write the same result in n dimension, and it's still true, you write it like this. Okay? Okay. Then he looked at if you have a function that grows Gaussian, suppose that regularity is not an issue. If the function is Gaussian, then the Fourier transform has to be at most Gaussian. If this one is power 4, this one should be power 4 third, right? Dual. Then what you have is this result, the following result. Another remark is if we define this is Gelfand, Shillop, if you have the functions in C, let's do it in 1 dimension to make it simple, that are entire, analytic everywhere, and are the functions that the Fourier transform decay, the real part decay as this one. Decay like this is this one real. And when you have the extension, you start to grow like as a power p here. And p is something between 1 and infinity. Then what Gelfand and Chilo prove is that if you take the Fourier transform of this, you get you have an entire function that have this decay in the real part, have that grow in the imaginary part. When you take the Fourier transform, you go to the dual, as you expect. But you have to be entire. Okay, let's for any question? Okay, let's try to prove Hormander's result. Okay, let's state that clear here, and you will see that we will be going to a setting that where all the techniques that we have cannot be applied. By the way, since they're expert about constants here, the result that I wrote here, that is Bonamy, Demanger, and that is sharp in one dimension, is open in higher dimension. Okay, let's prove the Hormander result. Let's prove the theorem. F in R1 in R if it was not in my original plan to prove this, but as I say, Didier asked for it. I don't. Okay. Okay, then to prove this, we need some result of in complex variables. Okay, first we need this theorem. All these theorems of this kind go Framman, Lindelof. Okay, suppose that it's a cone, vertex at the origin, opening pi over beta. Without a lot of generality, you can rotate things, and this is your cone. Suppose that F go from the cone into the complex variable such that F is analytic on the inside, F is continuous up to the boundary, and F is bounded in these two lines. suppose that there exists alpha between 0 and beta such that f of c is less than some constant, another constant, c to the alpha. Then this function grows at infinity for c in the cone, that is when you are defined. It grows at most with power alpha that is less than the opening according to this picture. Then the supremum everywhere is bounded by M. It's a kind of maximum principle. Okay, so let's see why you need all this. Suppose that beta can be 1. Beta has to be more than 1, by the way. Beta suppose that beta is 1, and you choose this function. Then you see that you are bounded when you are in the complex. When you are here, when the real part is 0, you are bounded, and then you have to kill this hypothesis, then you cannot decay linearly. That is why you are decaying. Right? Okay, you have to decay less than linear to apply the theorem. Okay, this is the enemy when you are with beta equal to 1. Okay, let's prove the theorem, because this is all that you need, except few tricks to prove Hormander and to prove Hardy and to prove all this theorem. Okay, this is the main tool. This is a kind of maximum modulo principle. Okay, how you prove this? You fix epsilon positive, and you fix gamma, a number between alpha and beta. And you define this function Okay, of course you are defined this power. This power may not be integer. You are defined, assume that this is your cone, and you are taking this, the log cutting thing here. Okay, this is the branch that you are taking. Then this function is analytic everywhere except this part in the negative real excess. This is analytic in the cone, then you are analytic in the cone. Let's see why this function is going to finish the proof of the theorem. Well, suppose that you take C equal to R e to the I theta. Theta is an angle between then what is the absolute value of this function? Is the absolute value of this and the absolute value of this one. Right? Well, the absolute value of this one by hypothesis is bounded by this for some constant C1 and C2. And this is R to the power alpha. Right? This is hypothesis here. And this one is exponential minus this. And this is the real part of this is the only thing that counts. Right? Because I have to put absolute over here. Then this is a cosine of this. Then if theta belongs here, gamma multiplied by theta belongs to this interval. And now you have that gamma over beta is less than 1 because this is gamma is less than beta, this is less than 1, then you are really inside minus pi pi. You are really inside this. You are far away from minus pi and far away from pi. Is this okay? Therefore, the cosine of this is bounded below. Therefore, theta in cosine of this is bounded below for some number that is positive. Then what do you have? This power is more than this power. Then for large enough, this quantity control this quantity. You are not far away from 0 here. Therefore, if you take this domain, very large, in this part, you're going to be as small as you please. What happened in this and this? Well, this part is absolute value less than 1, and this part has absolute value bounded by m. Therefore, you are bounded by m here, and as small as you want here. Then by the maximum principle, you are bounded by m everywhere. Then you have that by the modulus maximum principle, this function is bounded by m on the cone. And now you take limit when epsilon goes to 0, and you have this, the answer. For all epsilon. Taking epsilon goes to 0, we get the result. Is that okay? Okay, let's see how you apply this theorem to prove Hofmann-Mander theorem. Any question related with this? Question? No question? Okay. Okay, let's try to prove the theorem using that you have there. Okay, the first step is you define this function. You're in one dimension. And you are trying to prove that if this hypothesis, let's put we saw that the Fourier transform of this function is in self. We're going to see that the start implies that this is finite. That this hypothesis implies that this one is finite. What is the advantage? The advantage is going to be that this function g is the convolution of this one with the original f. This function is an entire function if you put c here. This function has an analytic extension to the whole complex plane. And it grows more, it's order 2. We will write everything. It grows at most like exponential of to c absolute value squared. It's of order 2. We will use that. Okay? Then you have more control about this g than about this f. Okay? By the way, this proof that I'm following is also bon ami de Manger and Janmin. Okay, let's prove that the hypothesis implies this. Okay, who is this? This is less. This one is okay, the G is the convolution with the Gaussian, that is this one. The Fourier transform of that is this one. And now we have integral here in C and X. And I forgot to put the 2 pi. Is this okay? This quantity that I'm trying to prove that is a consequence of the hypothesis is exactly equal to this one. And we are trying to prove that this is finite. Then this is less. Sorry? What do I have wrong? Yeah. Yeah. At the end, I will have something like this. Okay? Is this okay? But this... 2 pi... No, because I'm translating this into the definition. I'm saying I want to prove this. This, by definition, is exactly this part is this. This part is this one, and I copy this one here. I'm just translating this to that. Is that okay? I am saying that this quantity is exactly equal to this quantity. Is this okay?
Because in the first one you changed x and y, right? So g of y is, this is g of x.
Yeah, okay, okay. Now you are completely right. You're completely right. I'm sorry. This is dx, and now this is dy. Okay, thank you. Thank you. And now I have to go back to this. Thank you. Please correct me, because otherwise we will. Okay, now I'm okay. This is this function in y. You're completely right. This is this definition of this. I have this here. Okay, I want to prove that this is finite. Then this is less than this. Now I'm going to integrate this one in x. And what we're going to integrate in x is this one. Okay, I have copied this one. I have to copy this one, and I have to subtract this one. Then I have exponential of 2 pi y. Is this okay? I just copy all the exponential that I have here, this. Since I introduce this one, I have to put minus. Is this okay? This is y? No, this is x, and this is x. Okay, I add this one that I don't have it, and I put it here negative, and I put all the ones that I have here. If I prove that this is bounded, uniformly in C and Y, then we will have that this is bound. You are integrating everything positive and things reduced to the hypothesis. Then we have to prove that this quantity is bounded, thus regardless of who is C, who is Y. Is this okay? I'm trying to prove that the hypothesis implies this one, and we are going to work with this function. Okay? And we are going to prove that G is 0, but if G is 0, F will be 0, because if G is 0, this is 0, this is never 0, this is.
It might be once integrating y, right? Because there's x outside, there's c outside.
Okay, yeah.
So this integral that you want is maybe y.
This is in Y.
Can't remain there.
And this is in X. Okay. Perfect. Now it's okay, right? I have to have these two here. This is what I add. This is what I want to finish. This is the condition that I have, is this one, and have to be this one. Thank you. And this is uniform here in X. Okay, let's do this part. This quantity is less, what you have in the square is less than this one. See, what you have here is 2 pi c y minus x. Right? This is less than this quantity. Right? By triangular inequality. X minus y or y minus x, whenever you want to write it. So you're going to put absolute value. This is dy. Therefore, this quantity is less than this one. Is this okay? I'm trying to integrate this, and I'm integrating something bigger. Everything is positive. I'm integrating something bigger. Now, I can change variable, and this is a translation in x. Then it's independent of who is x. Then this is exactly. By changing variable. And now you have to prove that there is no x anymore. You want to bound this independently of who is C. Okay, but what is exactly that you're integrating here? Suppose that C is positive. You switch the absolute value here, then you integrate in some domain here. This quantity that you're integrating is equal to this, or is equal to this. Depending on if C is positive and Y is positive and so forth, but you're integrating this. And that integral is finite regardless of who is C. Therefore, we can start the proof here. Is this okay? Okay, we will start the proof here. Okay, so I have to. Okay, then. Can I erase this part? Okay. Let's see if we can finish this. Okay. Then we have to do some remark. G of x is the convolution of this function with your original function that is in L1. Then G have an analytic extension entire, can be extended to an entire function. And moreover, G of C is less than some constant exponential of C squared. Do you believe that? The fact that this is analytic is, well, roughly speaking, if you convolve to function, the convolution is as good, right, as any one of any one. You can add the smoothness. But this one have an analytic extension. Then you have that. And then you write what you want, the convolution, in the variable C, and you will see that when you plug it here, you will have this bound easily. I mean, you have this C1, C2 are positive. Okay, you are not in this decay, but when you put complex variable, the complex part grow, and this is exactly that you are bound at. You want me to prove this? No, because, I mean, you write this, the convolution, and you will see that very rough estimate will give you this. Okay. Then this is to say that you are entire of order 2. And of course, this is what you want to apply the Fragment-Lindelof theorem. Okay, the next one is that you define this function. Okay, and this is a trick that finishes the business. Why? G is entire. Well, it's the primitive of the product of two entire functions. Right? G satisfies something like this. Why? Well, because the integration is the length, and these one are bounded by some roughly like this, and you will see that you can, since you are analytic, you can do the integration in line whenever you want, and you will see that you have this. With another constant. Is this okay? I mean, this satisfies this bound, this satisfies this bound. The worst thing is how far you go, because all this thing is growing. Then this will be a linear growth, and this you put the last point here, and this is a very simple estimate. Right? Remember that you are integrating an analytic function. Sure. Okay. Notice this. What is G? Let me see, 1 second. 10, 11, 9, 9. Notice this. You have, who is G of C? G of C, okay. This function have exponential decay. Why? Because this f is in L1. This is a bounded function. These have exponential decay. Then, therefore, this function have an exponential decay, have an analytic extension. Therefore, you have that G can be written like this formula is okay. You can go back to this. Okay? But G decay very fast, then you can write this. This will give you the growth when you take this one, the complex part of this, multiply the I, but that will grow linear, and this one decay quadratic. Then all this makes sense. You have this estimate. Is this okay? Okay. Therefore, you have this. Take absolute value in psi. You have this. A very crude estimate, but this gives you the following. Suppose that you integrate g of x but the supremum of c complex number with the same absolute value than x, g of c, this x. Okay? Okay. What is exactly that you are integrating here? You are multiplying the g, evaluated in x, by this expression that is the supremum of the analytic extension of g over the sphere of radius absolute value of x. Who is this? This quantity is bounded by this one. Is this okay? Therefore, this is bounded by this. This, I can put supremum here. The only thing that matters here is what is the absolute value of this quantity. This bound only depends on what is the absolute value of c. Then if I put x here, I have this bound. And my hypothesis, this is my hypothesis, this is less than n. This is the hypothesis. Let's call this hypothesis to start. Then you have that if you multiply g against the supremum over all complex numbers that have the same modulus of the absolute value of x, and you integrate this in x, this is finite. This is the hypothesis translating to this. Right? Because you take supremum here in C, supremum here is to put here x. Then we have this estimate. Okay, now what does that tell you? What is this estimate tell you with respect to this one? G is bounded on the x's. Let's say y. Suppose that you choose C to be real. What do you have? You have the integral between 0 put absolute value inside g of u, g of I of u, du. Then you're integrating here. You can put this, if you want, let's call it t in this case. You bound the supremum of this with this. these two have the same absolute value. And you bound the supremum of this one over all the possibility. And you bound this integral between minus infinity and infinity. Therefore, you bound this when x is real. And if x is imaginary, then you will have it in this side and you have it in the other part. Then this function g has the property that you are of order 2, is entire, and it's bounded on the x's. This is, let's call this. If you do it in real and you do it imaginary, it's the same business. Okay, and then you want to apply the Franklin-Lindelof, and you are still not okay because, what is the opening when you have between two x's? You have pi over 2, and you are of order 2, you are in the limit. You cannot apply that. You need to have less opening. Remember that, okay? Okay, what is the last trick? Is this. Okay, last. For every alpha, you define this function g sub alpha of c, that is going to be the integral of this g of e to the minus I alpha u g of I u du. What is the only thing that you are doing with this function? The difference between this and this one. Okay. Consider this function in this cone. This is your cone. Then G is entire of order 2 but it will be bounded here and bounded here. And now your opening is less than pi, and you will be able to apply the theorem. Okay? We have to prove that it's bounded here and bounded here. Once, suppose that we prove that it's bounded here and bounded here with this constant given by this number. Then when you take alpha to, then you will be bounded by a fixed constant here, and you move the alpha, and the constant that you bound with is the same. Then this converges to this one, then you are bounded by m. Then the final one will be bounded by n in the quarter here. And you are going to do this in every quarter, then the g will be bounded in every quarter. You can do that because you have the same property in all the x's. And then by Liouville theorem, g will be a constant. But if g is a constant, this one that you are integrating will have to be a constant, then this g will have to be a constant, but since you converge it to goes to 0, you have to be 0. Then everything reduced to prove that this function is bounded by a constant that doesn't have anything to do with this alpha. Right? Because then you will have this g alpha of c will convert to g alpha with c in the first square. And this is bounded uniformly in alpha, then this will be bounded. Okay, then the only thing that we need to prove is that you are bounded in the x's. Okay. Then what is g alpha in I, y? When you are here. Then this is absolute value of I, y, less or equal g of whenever you put here Okay? Then absolute value of g of t dt. And now use this property. These have the same absolute value that this one. When you put the supremum here, this quantity is bounded even if you integrate the whole domain. You have that. And now what happens if you integrate here? Who is this? This is r e to the I alpha. Then who is g alpha r e to the I alpha? It's going to be less than the integral okay. Then now I use that you have minus alpha here, then this is going to be g of r, g of I r e to the minus or I alpha dr. This is the one that is going to be bounded because have the same absolute value that this one. And you apply this. You are bounded regardless who is this length. Therefore, you are bounded here. You are bounded here. This opening is less. You can take this b to b2, right? Because it's less than this. Then you can apply Fragment-Lindelof theorem with 2. And you finish. And then you have this property. You apply Liouville theorem that gives you this is constant. You do it, of course, you do this in every square. You have bound and entire. You have to be constant. Then this has to be a constant, and so forth. And you finish. But the only constant has to be 0 because you tend to 0. Then you can see that the proof is not too complicated. But I don't see how you can do a proof like this without analytic function. And this is one of the questions that we will go there. Okay? Okay, don't take the proof too serious because the question is not about any of this. But we will see that in a moment what kind of question we want to answer here. Any question related with this proof? Okay, let's go to really why do we care about this uncertainty principle and all this? What have anything to do with the Schrödinger equation? And we have time, we will see that you can ask questions we can ask an open question at the end of the class, and you will see why. Suppose that we have the free Schrödinger equation. Okay, we want to solve this. Then you take Fourier transform, and you commute since, and the Fourier transform of this will give you, because the derivatives will become multiplication, that you will have something like this. Then you have a family of ordinary differential equations that for each C you have, for each frequency you have an ODE that you can solve, and you finish that UC T is exponential of, do I have a, I think I have a minus, no? Because each time that you take derivatives is 2 pi I, right? And then there's a minus somewhere here. Minus I 4 pi squared T C squared U0. Therefore, U of xt is the inverse of this expression. Okay, now let's recall a few things that we did the first class to get the explicit formula here. Okay, let's forget that for the moment and let's recall what we did. I think that we proved this formula. I may have it written somewhere, or maybe I don't have it written anywhere. I think that we proved this. Do we have that one from the first class? Is that if A is positive, we have that? Are the constant okay, A? Remember that if A is 1, you recover that this function is his Fourier transform. Okay? Okay, then we prove this. Okay, notice that two things. As a function of A, we prove this only here for A positive, right? Now look this expression. As a function of A, this makes sense where? Whenever you can extend this to complex variable, whenever A, you can define this power. To define the power, you have to define the log, right? Then you cut this into this piece. Suppose that you're in one dimension, you can do this each component, right? Then this function makes sense everywhere here. And it's analytic. This function is analytic here. Where, go here. The Fourier transform of this function, then if the function has an exponential decay, then the Fourier transform is analytic. And this makes sense whenever this is still bounded. Then this makes sense if you put the real part of A is positive. This function, suppose that A is equal to alpha plus I beta, then you're going to have something like this, alpha pi x squared, something that decay and something that oscillate. Then the Fourier transform of this makes sense. This is still an L1 function. This gives you oscillation, but when you, right? Therefore, this is an analytic function in this part. But since both are analytic and they agree in a limit point, in fact, they agree in a line, they have to be equal. Right? In particular, if we take A equal to 4 pi squared IT, that means that you are here, pure imaginary, right? This is the extension. Then you have the right to say that e to the minus 4 pi squared, 4 pi squared x squared IT, Fourier transform of this, the function of C is 4 pi IT n half e to the minus, since the I is in the bottom, then you're going to have 4, the T, the pi die, and you have this. You can write the pi and the pi here die. You can put the I in the top and switch the sign. Okay? Therefore, what you have here, the solution, well, all these functions are even. The Fourier transform of this is this. The Fourier transform of this is this one. Okay, all these functions are even. You don't have to switch that. What you have is this. This is exactly the Fourier transform of this is going to be e to the minus c plus I 4t 4 pi t I n half Fourier transform of this u0 x t this. And now you use that this is exactly to put convolution of these two. And so for the product of the Fourier transform is a convolution. This is exactly e to the I square 4t convolution u0. Or, if you wish, okay, you can write it this way or you can write it this way. Okay, we haven't said anything that up to now make any sense what we did before, right? Okay, but look this. U of xt is the convolution of these two expressions is e to the I x minus y square 4t 4 pi it n half u0 of y dy. And this is equal. I develop this square here. Then you have the double product. Then you have 14 the double product gives you 2 pi, then 4 pi t. I'm writing this intentionally, right? And there is a minus. And then you have exponential of I y squared 4t u0 of y dy. Okay, I develop this square. This is the double product, and I put the double, I put the pi here, and I put the pi here. Okay, then forget for the moment this. Who is this? This is the Fourier transform of this function. Right? If I don't have this, this is the Fourier transform evaluated in the x variable, but I have this. Therefore, this is exactly equal to this quantity Fourier transform of this expression evaluated at the point x 4 pi t. Then, if you pass this to the other side, right? This have absolute value 1. This is a number. Suppose that t is fixed. Then you are saying that the Fourier transform, the solution is the Fourier transfer of the data by this factor that gives you oscillation depending on the t evaluated at this point. Okay? Then let's rephrase this in terms of the, for example, let's rephrase this in terms of the Hardy principle. What will be the Hardy principle? Hardy say if f of x exponential, for example, of a pi x squared and f of c exponential of e to the b pi c squared belongs to L2 of Rn with a and b positive. A multiplied by b larger or equal to 1 imply f is 0. This is Hardy in the L2 version. Okay, let's rephrase that in this term. This is your function originally. Suppose that you choose f. For you is this. E to the, well, now I have to be careful because, okay, is I x squared 40 u0 of x. Okay? And this is the condition. And who is your u? Your u in absolute value is some constant that depends on the dimension and t, right? The Fourier transform of this, evaluated at this point. Okay, and I want a condition on u0, what is the possible decay, for example, again, Gaussian's weight of u0 and the solution. Then, if I put this, u0 absolute value of x exponential of a pi x squared is equal to this condition. And the condition of this I want this condition in bed. Exponential of b pi, and I have the x here. I have to be careful because I don't have the Fourier transform. In x squared is equal to cnt, Fourier transform of this, x 4 pi t, e beta pi x squared. I want this in L2 and this in L2. Okay, what is the condition? I have to translate this, right, into, then this is equivalent, that this is in L2 is equivalent that this is in L2. I call y. Then you have that fy exponential x is 4 pi t y squared in L2. Then what is the condition that this will give you 0? This will give you 0 if a, anything that you put in front, a here, multiplied by b, multiplied by 4 pi squared, is more than 1. Okay? Then the condition is you have this theorem that said if the solution, if this is in L2, and this is in L2 of Rn, Hardy and A and B are positive, and A times B multiplied by 4 pi t is more than or equal to 1, then you are 0. All these uncertainty principle that we prove, you can rephrase that in terms of the solution of the Schrodinger equation. Okay, you just Just a rephrasing these things. 6. Okay, now let's go where the question starts. Let me give you some questions now. Suppose that you have the simplest one. Suppose that you have this. Let's put here B, and B can be just a function of x, or B a function of x or t. Suppose that you have U0 is compact support. It's infinity if you wish. What do you know about the Fourier transform of this? We know that if you start with a function that has compact support, the Fourier transform will never decay exponentially. Can you prove this? For which potential can you prove this? Now you have potential here. You are out of Fourier transform. Okay, this formula that is nice is over. Okay? Question. For which class of potentials can one show this property? That if you start with compact support, you will never have that. Of course, if you don't put the potential, this is true. I mean, if you don't have the potential, this is true because, right, these have compact support, these have compact support. Then this one will not decay exponential. This is not going to give you more decay or not. This is true if you don't have a potential. Is that true with potential? Okay. With respect to the Hardy, we proved in a joint work with Escabriasa Koenig and Vega, we proved that you can find potentials such that you prove this. Solution of this problem, if P belongs to some class, then you have exactly this. If the solution, if the initial data belongs to this L2 with this, and this belong here, and then you have that. You lose the quality. And that's its chart because there is some potential that you have that. But this is the Hardy one. Go to the extremal and ask yourself this question. Okay. Let me give you another question, since we are into the question business. And the problem is that we don't have enough tool to go into the proof. Then we will have to spend some classes building some techniques to understand some of this proof. But this is an open question, by the way. This is open. Put your favorite here, alpha minus 1. Suppose alpha, even odd integer if you wish. Is that bother you so far? And you put it in any sign. And let's put the sign that you have. Let's make this, prove this sign. What is the fastest possible decay of solution of this problem? What is the fastest possible decay that you can have that? Even for a short time, suppose, no global. Well, that's an open question. The only thing that you can say is this. Suppose that you want a solution, you choose this type of things, then you have W here. Then what you have is that you have IW is equal to I Laplacian of this plus phi alpha minus 1 phi. Then you forget that this. Then how fast this decay? The best answer at this point is that you have to be a solution of this selective problem. This is you look solution, and this is look for a standing wave solution of this. Then in a space, this gives you just oscillation. How fast you decay, suppose that how fast you decay, how fast the solution of this problem decay. And these are linear exponential. But this is because you are tricking yourself. You want to reduce this to something that is stationary. I mean, can you prove that this is the best possible decay, or can you construct that? Well, since we are into open problem, let me give you another one that is even a little bit more discouraged. This is an open question, by the way, open. And this is what is known. And what is known is that phi of x decay like exponential to c of x. And since we are into the elliptic, and this is by no means the idea of these lectures, but let's see, even go to the simplest problem in elliptic. Suppose that you have a potential that is infinity. I'm sorry, L infinity in Rn. Suppose that you ask this question. What is the fastest possible decay that you can have of that problem? By the way, B is bounded, then you can write B of x like B1 of x plus lambda, and then you are solving an eigenvalue problem and so forth. Okay. Then it was, I think, Landis who conjectured that the following: if for all A positive, Landis conjectured this. Maybe not explicit, but it's in one of the papers. That if you decay against any linear exponential, this way you want to put a 2 here, is that bother you? doesn't matter. Then you have to be 0. Okay? Then Meshko proved that this is false. Proof that there exists B complex valued such that solution of this and he proved if for all A is finite, then you are 0. F 4/3 is the limit business. Then the question is, if you solve this eigenvalue problem with a potential here, you can write it this way or not, whatever you want. Then the conjecture was that you cannot decay more than linear. If you want, prove epsilon here if you wish. Anything that is close to linear will do it. What is known only is to 4/3. For this one, you need the potential to be complex value. Then the conjecture, it still makes sense if you say that B is real. This is what people believe. If this potential is real valued, then you should decay at least, at most linearly. And if you have complex potential and you have said this, the problem has been completely solved, you can get until 4/3, but no more than 4/3. And we will prove this. Even that we don't want to, we will prove it because it's something that will appear as a consequence. And 4/3 is extremely natural. It doesn't look natural now, but it's the right power. Then you can see that even in elliptic linear problems, things are unknown. Then if you go here to know of evolution that have to do with stationary, this is known. You know exactly how this one decay, but you don't know how this one decay. And even in the linear problem with potential, these kind of things are not unknown. Then what we want to do to begin with, maybe next time, is to develop some techniques to be able to approach problems that have potential. Then the first naive approach will be this. Can you prove Hardy principle without using analyticity? That will be the first approach. Forget about potential. Do it linearly with free Schrodinger equation, but don't use analyticity anywhere. That will be this very naive approach. Right? Second is, try to understand the decay of the Schrodinger equation. How this Schrodinger equation precedes decay. Well, if you have then the decay, if the decay are polynomial, then this is well understood. If the decay are exponential, then you start to run into trouble. And we will see why. Okay. Then this is what we will start next time. And then this question, this is decay in time, and you can ask this for a short time, or you can ask this for a global time. Okay? And when you ask for a global time question of this, so this kind of question will appear if you start with potential. Okay. Then what we will do now is to start with develop some techniques to be able to approach that. Okay, which are the techniques? It will be kind of, boring for most of you, but we will have to do some harmonic analysis, right? There is Hilbert transform, maximal function, and maybe we will take 1 or 2 classes of this. Okay? Okay, since we have plenty of time, let's do something with the Hilbert transform. At least let's motivate what's the Hilbert transform and all this. And we get rid of this. Okay, then by the way, the same question is valid if you put for example, or for any, the thing start to be simple if you put the KdV. For a strange reason, for the KdV, the answer what is the idea of the decay? Let me go back and explain this. This question that we state here for the linear KdV or for the nonlinear one has been answered. And the thing is that the KdV, the fundamental solution, have exponential decay in one side. Right? Then in some sense, you cannot expect anything to decay better than this exponential, and you can construct solutions that decay for short time as the fundamental solution and so forth. The problem with the Schrödinger equation is the fundamental solution doesn't decay, it's just oscillation. Then it has to do with uncertainty principle, completely different matter. Okay. Okay, let's try to go to the okay, since before we go, let's go even, since we are into the decay business, let's go to the Benjamin-Ono equation. That is a dispersive equation, and this is equation, I think it can be written in this way. And you ask yourself, how fast, the same question for the Schrödinger, how fast the solution of this can decay? Okay? Okay. Let me define R. So F okay, these are the functions that have k derivatives in L2. Okay? Okay. In some sense, for all these dispersive equations, if you want to preserve decay, you need regularity. Okay, we will make things more precise in a moment. But okay, what Iorio proved was the following. If you start with the regularity that you wish, let me state that in like this. Suppose that you start with a Schwarz class, a data. Then, if any, then it's not true that x to the power 3 use of t belongs to L2. In fact, this is false. If you are in the Schwarz class and you ask for this data to have mean value 0, then this is true. Is that okay? Okay, what I'm not putting the top right, with all detail. What he says, doesn't matter how regular you start, how decay you want, compact support, anything. If you don't put any condition, it's not true that you have power 3. It's L2. If you put this condition, then you can go to power 3, but not to power 4. And that's it. Doesn't matter what condition you put here, you cannot avoid this. Then you have that the problem with here is not the exponential or anything like this. It has to do with pure power. Okay, have completely different business. Okay, what we are going to prove is something in the middle. You are okay up to 3 plus 1/2. But you are okay like this. And now I don't remember if the 1/2 is included or not. I should know that, but I don't remember. Yeah, I don't think this is okay. If you put this condition, you should be able to say that you decay like this, but you don't decay like this. Then 1/2 is, this is the cottage age of that, okay? You can see that then it's a completely different question. The Benjamin Ono, the KDV, and all this, and even that you are working with dispersive equation, they are different. Okay, let's forget this. We will see this in the last part of the classes, the last part of the course. And for that, and even for the purpose of understanding the decay of the Schrödinger equation, we have to understand the Hilbert transform. Okay, and then let's try to make the Hilbert transform. What do we need today for the Hilbert transform? Okay, the Hilbert transform is, where does the Hilbert transform appear? Okay, suppose that you solve the following Dirichlet problem. You want a function that is elliptic. In the upper half semiplane, and you have prescribed value. Suppose that this is in L2. Okay. That means you have f, if you want real value. It's prescribed here. You want to extend this to a function that is harmonic in the upper half plane. Okay. Then you take Fourier transform in the x variable. Therefore, this then this commute, and then this is exactly what we did before. Is therefore the solution of this, you can write this ODE in many ways. Is that okay? Yeah, right? Okay, but you can write the exponential and so forth, but then you have to be careful because you need this to decay. You cannot write it exponential like this. Then the appropriate way to do it is to write it in this way. That will do it or not? There is no t here. This is y. This is y, and this is u0. Then this solves the problem, right? If you want the other solutions, remember this is an order 2. You have two solutions. The other solution will be this one. But you don't want that one because it grows too much and you cannot take Fourier transform. Therefore, your u of x, y is this. And then you remember what we said in the first class, it was this, that the Fourier transform of this is this one. And the other way around because they are even functions. Therefore, this is exactly, and you use the fact that if you have the dilation of f of x is f of ax, the Fourier transform of this is 1 over an f of c over a, like this. Therefore, what you have here, when you take the Fourier transform of this, you're going to have one over pi 1 plus 1 over x squared convolution with u0, but then we have to do the dilation of this. This function has to be evaluated in 1. You have the y here. Then this is going to be, if I multiply by y, this is y over y, that x squared. Is that okay? Then this is a convolution. Then this is 1 over pi y x squared plus y squared convolution in the x variable with u0. And this is the Poisson kernel of something like that. This. That means that this is 1 over x integral between minus infinity and infinity y x minus t squared plus y squared u0 of t dt. Okay, this is the harmonic extension of the f. I'm sorry, there is no u sub 0 anywhere here. F, 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 F. Okay. And this is a nice kernel. This is a nice kernel. You have total area 1. This is a rho of x. Rho y of x is 1 over y, rho of x over y. And this is positive. We have integral 1. And it's a good approximation of the unit. Is this okay? Okay, then you go from f, you go the harmonic. Okay, who is the harmonic conjugate of this? Well, you are taking convolution with this kernel. Then, in the complex sense, this look like 1 over c, right? If we write here 1 over c, you never write 1 over c. You have to rationalize this. You have c squared. Then this is x minus iy, x squared plus y squared. Then you are taking you multiply by I. If I want to take the real part, then I put I here, and I put I here, put I here, and this is going to be I plus ix, x squared plus y squared. Then this is exactly the 1 over pi, the real part of this. This quantity is the real part of this expression. Then, of course, this function is analytic as it is 0, therefore the real part is harmonic. Then if you convolve, you preserve all the good properties, this will be harmonic. then if you want to find who is B, you take the imaginary part. Then the kernel that you have to take is the imaginary part of this. And the imaginary part of this is this one, this kernel. Therefore, the B, that is harmonic conjugate, of U is just convolution with this kernel in the x variable. Then it's 1 over pi integral between minus infinity and infinity, x minus t squared plus y squared, right? And then you have f of y. Is this okay? Then this function is harmonic because it's the imaginary part of something that is analytic. You are in the upper half plane. This is harmonic. And this function is analytic. The problem is that this is a bad kernel. As a function of x, let's put y equal to 1. Okay, you do the dilation in y. This is a bad kernel. Why this is a bad kernel? Because it's not positive to begin with. It's not even in L1. Okay, it's have all the good property that you have for this one, you have none here. It's not positive, it's not in L1, nothing. The only good thing that you have is that this is odd. Have mean value 0. If you integrate. Okay. Very roughly speaking, what happens when y goes to 0 here? When y goes to 0 here, you will go into this. Right? But you have to be careful in which way you go with this. Then what is exactly that you are doing is you take your f here, you have the harmonic extension of this, you have the conjugated, and I'm trying to go with this one to 0. I'm trying to see what I recover here. And what you recover here is the Hilbert transform. And who is the Hilbert transform? Well, you have to make sense of what you're doing here. You are taking this limit, go here. Then this is the principal value of this quantity. You're going to take the principal value of this quantity means that you are taking into consideration that you're going to take first that this one is odd. Then the Hilbert transform that you have here is this. The Hilbert transform of f of x is 1 over pi, the principal value of 1x convolution f. And what is this? This is 1 over pi, the limit, when epsilon tends to 0, of the integral y more than epsilon less than 1 over epsilon f of x minus y over y dy. That means what you are doing here is you fix your epsilon, you put 1 over y that is not a good function because it's not in L1, but you truncate at 0 because this is not in L1 at 0. You truncate at infinity, and you use that this function, right? You have some cancellation, and that will make sense of this. Next time, we will see that this makes sense, and we need some property of the Hilbert transform to be able to compute the decay of the Schrödinger equation and into the Benjamin-Ona equation. Okay? Okay, let's stop here. Any question?